Okay, so in this video we're going to talk about ionization constants, and in your textbook this is chapter 17, sections 3 and 4. Now before I get into ionization constants, I want to remind you that with a strong acid or base, it's going to dissociate completely. So that means that if we have something like HCl, it's not like everything's in equilibrium, right? And it's going to form H plus and Cl minus. But this reaction, this dissociation happens so intensely in HCl that the reverse reaction doesn't really happen. It's all going forward. But that isn't always the case. There's some weak acids out there. And when you have a weak acid, you have to do some special things when you're going to try to calculate out like pH or find out what the equilibrium is and all of that. And so that's what this video is really going to get into. Okay, so a weak acid, right, incompletely ionizes. And so the full molecule and the ions exist in equilibrium together. So if you have a weak acid that we generally will call weak acid HA. So if we have HA and it's aqueous, meaning that's in water, it's going to be in equilibrium with its conjugate base, A minus. You'll also sometimes hear this be called like the salt of it. So A minus and the hydronium ion, which we can take this reaction and like take out the water and change the hydronium ion into just a proton. Both works. And then with a weak base, remember a base is one that takes a proton. So we'll have some base here with water, and it's going to be in equilibrium with BH plus because it's taken on that proton, and OH minus hydroxide. Some examples of these, acetic acid, what you're actually going to be testing for in the next lab, dissociates into H plus and acetate CH3COO minus. And it doesn't do this completely. It does it at about 1%. So that means that if you put 100 molecules of acetic acid into water, one of them is going to dissociate. An example of a base would be NH3 with water. Oops, that should be H2O. In equilibrium with NH4 plus ammonium and OH minus hydroxide. All right. I forget the exact percentage that one dissociates at, but that's the idea, right? We see some dissociation in it, but not complete. All right. So the key things in a weak acid-base equilibrium are we have the acid with water, and then its conjugate base with the hydronium ion. And then this is like the general reaction. So let's write what the Ka is. So remember Ka, anytime we see that big capital K, we're talking about the equilibrium constant. So you can also think of Ka as Kc. It's the same idea, it's just that when we put that A, we're specifically talking about an acid. And so we put the concentration of the products over the concentration of the reactants. And if either of these had coefficients, then remember you would put the coefficients up. Okay, so then remember that the concentration of water is constant. So we're going to rewrite this to be that Ka is equal to the concentration of our conjugate base times the concentration of the hydronium ion or H plus, both work, over our concentration of HA. So that's our acid ionization constant, and that's the general formula for it. So we have this simplified version. Oops, this should be So there should be there. This should say A minus. So right, we said that Ka is equal to our concentration of A minus times our concentration of H plus over our concentration of HA. So similar to how we use pH to talk about the concentration of H plus, we sometimes talk about pKa. And this, it's just a way to make it easier because the Kas can be weird numbers. So using pKa, we're able to get more concise numbers essentially. Whenever you see P and then something else, what you're saying is you took the negative log of that value. So Ka also, if you know the pKa, you can find the Ka by taking 10 to the negative pKa. Alright, so these are the three main equations you'll want to know with pKa and Ka for an acid. It's the same equation for a base, it's just that as a base that it will be very, very tiny. So let's take a look at some of these values. So if we look at iodonic acid, HiO3, we can see that it has a large dissociation, right? Its Ka is basically 0.17. So its pKa comes out to 0.77. So that means that a lot of it dissociated, a lot of it went away. So the smaller the pKa, the stronger the acid. And you can see that as we go down, the acid becomes weaker. So some examples, hydrocyanic acid, right? It's a very small Ka, meaning that it's not going to dissociate very much, and so then we see a large pKa. So remember, the bigger the pKa, the weaker the acid. The smaller the pKa, the stronger the acid. Okay, so let's do a little learning check with this. So if we do, we want to know what the pKa is of HF if Ka is 5.3 times 10 to the negative 4. And then here you see the two equations for it. So just as a reminder, Ka is our concentration of our conjugate base, F minus, times the concentration of H plus, divided by our concentration of the acid, HF. And that equals 3.5 times 10 to the negative 4. So to find pKa, we're going to take the negative log of that. And we get 3.46. So it's on the strong side of a weak acid. Okay, so there's two ways that we can look at a reaction of weak base with water. First is by taking the conjugate base of an acid, so like the acetate ion, and react it with water to then reform the acid and produce OH minus. Another way is by having an actual base, so like ammonia, and have it react with water to form NH4 plus, or ammonium, and the hydroxide ion. So you can see in both of these the hydroxide ion is being formed. So if we want to find Kb, so just like we did with Ka, so Kb is really talking about the equilibrium constant for a base, or the ionization constant, right? They're kind of the same idea. Because the ionization is talking about how much is it ionizing, which is really, it's really just where is it in equilibrium. All right, so Kb, if we look, right, and we're going to do the general one, is going to be our concentration of BH plus times our concentration of OH minus divided by our concentration of the base times the concentration of water. And then remember, water is a constant. So we're going to rewrite this as the concentration of our conjugate acid times our concentration of hydroxide divided by our concentration of the base. So, right, and then same thing as you do with pKa, you can find pKb. And to do that, you take the negative log of Kb. That should be a B, not a P. There we go. That should be subscript. Okay. So let's have you give this a try here. Why don't you find the pKb of C5H5N? Okay, so what you should have found for the pKb is 8.76. Hopefully you got that. It shouldn't be too hard of a problem. So similar to pKa, pKb can tell us how strong or weak an base is. Sorry. So again, if the pKb is small, then that means it's a strong acid. And if the pKb is large, then it's a weak acid. So this can give us it's a very weak acid. So this can give us an idea of how strong or weak an base is, or how the conjugate base is. All right. So there's so remember with conjugate bases, we can find the Ka and the Kb. Right? So if we have a generic acid in water, right, this is the Ka, and then if we take the conjugate base in water, that's the Kb. And so let's look at what happens when we add these together. So if you look, right, we can cancel out things that are on opposite sides of the line when we add equations. So we can see the conjugate base is on opposite sides of the reaction line, and the acid is on opposite sides of the reaction line. And so what we get is 2H2O is in equilibrium with H3O plus and OH minus. Oh, look at that. It's a water equation. And so what we can see then, if we take Ka times Kb, that's equal to our concentration of our conjugate base times our concentration of H plus divided by our concentration of our acid times the concentration of the acid, because we're doing Kb now, times the concentration of OH minus divided by A minus, the base. And so if you, right, standard math, you can cancel things that are on opposite sides of the line when you're multiplying. And so we get that if we multiply Ka plus Kb, we should get H plus times OH minus, which is also Kw. And so that means that Ka times Kb for any conjugate acid-base pair is going to equal Kw, which is 10 to the negative 14 at 25 degrees Celsius. All right, we can look at this with, in terms of doing logs of it. Remember, if you multiply logs, that's like adding logs. So if we want to find what the pKw is, right, that's going to be the negative log of Ka times Kb, because we already said that's what it is going to equal the negative log of Kw, which should equal the negative log of 10 to the negative 14. And so that means that the negative log of Ka plus, or sorry, not plus, minus, minus the log of Kb, right, we're using this idea up here, is going to equal the negative log of Kw, which is going to be negative times negative 14. So that means that Ka, because that's what the negative log of Ka is, plus pKb, because negative log of Kb is pKb, equals pKw, which will equal 14 at 25 degrees Celsius. So remember that earlier we learned that the inverse relationship of So what we see here, right, is that the conjugate base pair should have an inverse relationship. And so that'll mean that the stronger the conjugate acid, the weaker the conjugate base, or vice versa. And you can use this as a way to get an idea of how strong the conjugate base is or how strong the conjugate acid is by looking at the pKa or the pKb. Okay, so now that we know what all of that is, we sometimes have to do calculations for finding this, not just as simple as what we have been dealing with, right? So we need to find a strategy for dealing with weak acid-base equilibrium calculations. So there's two general types. The first is calculating Ka or Kb from the initial concentration of acid and measuring the pH. And the second is calculating the equilibrium concentrations given Ka or Kb and the initial concentrations. We're really only going to get into the first type today. The second type we'll get into later in the unit. So let's get into it. Okay, so if we want to find Ka and Kb from the initial concentrations, we need to recall some things about equilibrium, right? So that means that we need to look at where the reaction is compared to the equilibrium constants, right? So that's when we compare the reaction quotient Q to Kc, and at equilibrium they should be equal. And we can either be given initial concentrations and one equilibrium concentration. And typically that equilibrium concentration is going to be pH or POH. Something else that can happen is you can be given initial concentrations and percent ionization. So you have an idea. Percent ionization is the moles of ions per liter divided by the number of moles available. So right, when I said that acetic acid dissociates at 1%, that would mean, right, when I said, oh, if you put 100 moles of it in solution and 1 mole of the conjugate base comes out, then and we multiply by 100, right? Then that would be 1%. So you're either going to be given this information, or you'll be given the percent ionization and initial concentrations. Okay, so let's do a problem here. So niconic acid is a monoprotic acid and has the following formula. A solution that is 0.012 molar in niconic acid has a pH of 3.39 at 25 degrees Celsius. What are the acid ionization constants, Ka and pKa, for this acid at 25 degrees Celsius, and what is the degree of ionization of the acid in solution? And so here we can see what the chemical equation is for this dissociating. So let's go into solving it. Remember, ice tables are back. So we wrote out the Ka here, and we put in our initial concentrations. And so if we want to find out, right, to find what Ka is, we need to find out what the concentrations are at equilibrium. So we can see that all of the compounds in it are 1-to-1. So we know that we're going to get minus X of our acid and then plus X of our conjugate base and plus X of the hydroxide ion. So that means that we're going to have this as our equilibrium concentrations. So to find out what X is, you're kind of, in other problems you'd be like, well, we can't figure out what X is unless we know one of these, or we know K, our equilibrium constant. But we do know one of these. We know H plus because we know the pH. So to find the concentration of H plus, you take 10 to the negative pH. So we do 10 to the negative 3.39, and we get 4.1 times 10 to the negative 4. So that's our X value. Okay, so let's write this into our table. So our X, right, is 0.00041. So if you do the math here, you get, this stays at pretty much the same value, because C initial here then is going to be much, much greater than Ka, because we can see that with how small of a change it's creating. But we get this here. All right. All right, so then we're ready to calculate Ka, because we have these we have all of our concentrations at equilibrium. So Ka is our concentration of C6H4NO2 minus times our concentration of H plus divided by the concentration of the acid, HC6H4NO2. And so remember that these two are the same value, so we can just do 0.00041 squared divided by 0.012. And if you do that math, then you will get 1.4 times 10 to the negative fifth. So we can see that Ka is really small, and so we can understand why it didn't dissociate very much. So then to find the pKa, we're going to take the negative log of 1.4 times 10 to the negative 5, and we get 4.85. Okay. And then it also asked us to find the percent ionization. So remember, that's going to be the moles ionized divided by moles available times 100%. And these are per liter. So really, we're talking about molarity. So for this one, what we're going to do is X over C initial. And so that's 0.00041 divided by 0.012 times 100%, and we get 3.4%. So almost 3.5 of the acid ions dissociate, or acid molecules dissociate. Okay, we can also calculate equilibrium concentrations from Ka or Kb and initial concentrations. So any problem where you get Ka or Kb will fall into one of the categories. The first is the only solute is a weak acid, or the only solute is a weak base. And so these two, right, because you're given initial concentrations and equilibrium value, it's just like solving it like we did last unit. So you build your ice table and you solve for X to figure out what the equilibrium concentrations are. Something else sometimes happens, though, where you're given two solutes. One is the weak base and the other, or the weak acid, and the other is its conjugate base. And this is actually a buffer problem that we'll solve later on in the unit. All right. So I want you to give this a try. This is similar to the first one we did. And I'll give you the answer here. So I'm not going to walk through it or read it to you. You can just pause and try to solve it and see if you get the right answer. All right, so that is ionization constants.